Okay, so we have discussed about two concepts. One is verification and another one is decision version of a problem or decision problem. Now to understand NP completeness, you need one more idea that is called reduction. So what is reduction? From the name you can understand it is reducing one problem into another. Reducing problem A to problem B, or transforming one problem into another problem. So how can we transform one problem into another, or why do you want to transform? Right. So we'll understand that. Fine. So here, understand this first. If we transform problem A into problem B, and if we say A is hard, then that will imply that B is also as hard as A. Okay. But the opposite is not true. And one more is, if we say A implies B, if B is easy, that will imply A is also easy, or A also should be easy. Okay. Why this opposite is not true? If I say B is hard, why that does not imply A is also hard? So we'll understand that. But this is transforming. This is a existing problem. This one is a new problem. So we are transforming existing problem into new problem. And we are saying if the existing problem was hard to solve, the new problem also must be as hard as existing problem. Okay. So that we are saying here. And this concept we are calling as reduction. Again, A is hard, known problem. This is new problem. And if A reduces to B, then B is also hard. So let us understand with an analogy. Think you have a remote in your home, and it's a powerful remote. Okay. It is a old or existing remote, powerful. Powerful means it can control multiple devices. Let's say it can control 4 devices. Okay. Now, and call it A. Now you bought a new remote. Let's call it B. When can I say B is as powerful as A? We can say B is as powerful as A only if whatever devices was controlled by B can also control those, right? So whatever A was handling, A's input can be reduced for B. Then we can say A is as powerful as B, because B can control all the 4 devices, and additionally it may control more devices. So B is at least as powerful as A, right? Now think opposite direction. We prove that remote B can control. We take whatever B can control and we say that A can also control those. Then can we say the same sentence now, that B is as powerful as A? No, because A can control that, but A can control any other extra devices also, we don't know. So when I am going from, say, I cannot say in the opposite direction, that if B control this, B is as powerful as A. That is not true. Okay. But if I say whatever A controls, B can also handle, then A is as powerful as B. But if I say whatever B handles, A can handle, we cannot say B is as powerful as A. So that is, sometimes you get confused. You remember this analogy. Then when we are reducing A to B, so whatever input of A, B can handle that. Right? So if A was difficult to solve, B must be as difficult as A. But opposite is not true. If I say B was difficult, I reduce A to B, I cannot say A was as difficult as B. So the direction is important here. Okay. So we take a difficult problem and we so that this problem can be changed to another problem. And the algorithm that solves B can solve A also. So let's look at an example here for more concrete understanding. Okay, so we'll take these two problems. One is your subset sum. Assume this is our known problem. And the another problem is we'll take is knapsack. This is a new problem. So we want to do reduction. Reduction means I'll take instance of subset sub problem and I'll convert into instance of knapsack problem, and we'll show that if we solve it with knapsack, we can get solution for subset sum also. Okay, so that is if knapsack can solve it easily, because I am converting subset sum problem into knapsack problem, and if knapsack is easy, can solve it easily, then subset sum can also can be solved easily. Okay. But if subset sum was difficult to solve, knapsack cannot solve it easily because I am converting this problem into the knapsack problem. Okay, how we'll do that? So subset sum problem we know, given a subset and a target. The question we ask, is there a subset whose sum is equals to the target? And how do we solve it? We can come up with all possible subset. We can take all single items or 2 items or 3 items, and we can test. And we know there are 2 power n subsets, right? And we need to evaluate all to find the solution. So this is a exponential time algorithm to find solution. Okay. Now, can I take this problem and convert to knapsack problem? So in knapsack problem, we know that you will be given some items, weights and values, and the question you ask, and a knapsack or a bag with capacity some W, and question we ask that without exceeding the capacity, what is the maximum value we can gain? Okay. Or decision version of the problem ask, is there a solution with value k? Right. So how we can reduce a subset sum problem into knapsack problem. So we'll reduce it like this. So our subset sum problem, we had, these are the elements 3, 5, 7, 10 and 15 is the target, and target is 15. So for knapsack problem we need weight, we need value, and we need a knapsack capacity W. So what we'll do, we'll say whatever the items were there in subset, we'll take exactly those items as weight, and also we'll take same thing as value also, and the target will take as capacity. Okay. Now the question we'll ask here in subset sum, we are asking the question, is there a solution subset whose sum is 15? Okay. So that answer is yes or no. In knapsack we'll ask the question, is there a solution with profit or total value equals to 15? Yes, no. Okay, and we'll see if you can answer this question, that whenever there is a solution, then we'll answer this question also will be yes. Whenever there is a solution for the knapsack problem, there is a solution for the subset sum problem, and there is no solution for the knapsack problem, there is no solution for the subset sum problem. Why is that? Because here when we are selecting the items, right, the profit is exactly equals to weight. So if I select suppose 3 and 5 weight, profit also will make 3 plus 5 10, right? Or if I select 5 and 7, then profit is also 5 plus 7 12, right? So if you want the profit to be 15, so the weight also has to be exactly 15. So for which selection we will get that? We see we can select 10 and 5. So we will get 10 plus 5, 15. So yes, there is a solution for knapsack where profit is equals to 15, yes. And we can see that is the solution for subset sum also, 5 and 10, right? That will be equals to a target. So the thing is, we took a subset sum problem, we converted it into a knapsack problem, and whenever this knapsack problem has a solution, then subset sum problem also has a solution. If knapsack problem does not have a solution, subset sum problem also does not have a solution. This is we'll call as reduction. We took a problem A, we reduce it to problem B. If an algorithm can solve problem B, the algorithm can be used to solve problem, means that will give me the solution for problem A also, right? This is the concept of reduction, right? Same thing is given here. Yeah. So we have reduced subset sum to knapsack, or we have changed a subset sum problem, or we have transformed a subset sum problem into a knapsack problem. Okay. Now, if knapsack problem is, there is an algorithm that can solve it efficiently, then we know any subset sum problem we can convert into knapsack. That means there must be algorithm that solve this also efficiently. Yes or no? If, think the other way. If we know this is a hard problem, there is no efficient solution for this, and we are saying we are converting into an knapsack problem, then there cannot be an efficient solution for knapsack, because if there is efficient solution, this also will be efficient. Why it will be hard? So we argue based on that if this is a hard problem, if we can transform it into an knapsack problem, this also must be a hard problem. Otherwise, if it is easy, this also an easy. But we have already proved, it is already proved that this is hard. So knapsack must be hard. Right? So that is true for any problem. If we take any problem A, if we reduce it to B, if A is hard, B must be as hard as A. If B is easy, we can solve B and get solution for A, then A also must be easy. But already we proved A is hard. So this is the technique of reduction we use to prove any new problem is hard problem by taking an existing problem and reducing it to a new problem. Okay. So if we can solve knapsack efficiently, we can solve subset problem also efficiently. But as subset sum is hard, knapsack also must be hard. Okay. So that is only shown here. We take the input for some problem L1 and we transform it as an input for problem L2. Like we took the subset sum and transform it for the input for the knapsack. And this transformation must be polynomial. It should not be exponential. That is, I change this in polynomial time into this problem, and then whenever this answer is yes, L2 problem answer is yes, L1 problem answer is also yes. L2 problem answer is no, L1 problem answer is also no. That way, using algorithm for L2, we devised an algorithm for L1. And this algorithm for L2, if it is efficient, then algorithm for L1 is also efficient. Otherwise, if L1 was hard, this cannot be efficient. Right? So that way, we call it as reduction, reducing one problem into another to prove the difficulty of an existing problem. So we'll look at one more example for this, where we'll take the proven problem like SAT, which is proved to be difficult or hard, and we can take a new problem like finding click, and we'll prove this is also, we can reduce SAT into click. Click is also difficult.